In this video, we're going to take the stuff you learned at GCSE, and hopefully saw in the last video, to the next level. Exciting. We're going to look particularly at magnetic flux and magnetic flux density, which are two important concepts we'll need as we go forward. First of all, let's look at magnetic flux density. It has the symbol B, and it's defined as the amount of force on a 1 meter of wire with 1 amp flowing through it at right angles to the magnetic field. What does that all mean? Well, imagine we had a north pole here and a south pole there. We've got a magnetic field here. We have 1 meter of wire going through here with 1 amp flowing through it. Well, how much force you get? We'll tell you the flux density, the magnetic flux density. It makes sense. The stronger those magnets, the stronger the field, the stronger the flux density. We're going to experience more force on that wire. If we turn that into an equation, well, the force is going to be equal to the magnetic flux density times by the current, times by the length of the wire in the field, and times by the sine of the angle between the wire and the field. You might be wondering where that comes from. Well, if you think about it, if that wire is not exactly right angles, then we need to consider the component that is involved in experiencing that force. That angle there between the wire and the field takes that into account. We'll see in a bit more detail in a minute. If we write it in symbols, there they are. Remember that B is the symbol for magnetic flux density. I, as we know, is current, L is length, and sine theta refers to this part here. Rearrange that, we get B equals F over IL sine theta, which is your definition, the amount of force per 1 amp per 1 meter, and then that takes into account the fact that it may not be right angles to the field. If we do sine of 90, like it has in the definition, sine of 90 is 1, well, it becomes that, which is your normal equation, which is the equation you often use. Interestingly, also if it's parallel to the field, so if we have that wire that's going through the field, we turn it around so it's parallel to the magnetic flux, sine of 0 is 1, and that disappears, because now the angle between the wire and the field is 0, we experience no force. The units of magnetic flux density, Tesla got there first, unfortunately, so it's named after him, capital T to represent Tesla. It can also be thought of as equivalent to that. What does this visually mean? Well, magnetic flux density is kind of how many field lines you have in a unit area. You can think of it that way. We've got two areas here on the left and the right. You can see that one here has a much weaker magnetic field, or much less magnetic flux per unit area. And that can be useful at times. How could we investigate these factors? Well, we can set up some sort of apparatus like this, which looks really cool. We've got a battery going through an ammeter to measure the current, because that was in the equation. It goes through into a magnetic field here and through a conductor. That conductor is stuck to a rod, that conductor is a rod stuck to a piece of wood or something, so that it can apply a force onto this balance. The current then comes out the other side through a variable resistor, or rheostat as they're also known, which can be used to vary the current. This has to be a non-conductor because otherwise it will conduct through here. As the current flows through this conductor, and we can measure the length of that in the magnetic field, it will experience a force. We can use Fleming's left-hand rule to work out the direction of that force. The current's going into the page like that. The magnetic field goes north to south like that. So the force is down. So this, as the force gets bigger, this is going to measure that force. So how can we do this? Well, watch this. If we are to vary that variable resistor, we could actually get some values for the amount of force in newtons on that balance. Remember, it's currently measuring a mass, so you're going to have to convert that into a force, a weight. And the current in amps. So remember, we'll get, when there's 0 amps, we might get 0 force. When there's 1 amp, we might get 1, and so on. Who knows? You measure it and write it down. Now, why is this interesting? Well, we can actually work out B from this. Remember, F equals BIL sine theta. Good news is, and I'll show you in a minute, when we set it up so the conducting rod is right angles to the field. So this becomes 1, and there's not of interest. If we now compare that to, you know what's coming, y equals mx plus c. If we plot F on the y-axis, we can plot I on the x-axis. F and I. What should we get? Well, there should be no intercept. The C should be 0, so it should go for the origin. It's going to be a straight line and positive like that. The gradient, N, well, it's going to be equal to B times L. That's great, because L is very easy to measure. We can just measure the length of that conductor in the magnetic field, and therefore we can work out the magnetic flux density, which is really useful to know. And we can do investigations related to that as well. So that's what you can see in here. That length would be that length there. Right, magnetic flux density is useful, but sometimes we're going to have a certain area and we're going to want to know how many field lines there actually are. Not how many field lines there are per unit area, per meter squared or whatever, but how many field lines we've got as an absolute number. And this is given this symbol here. The units are the Weber, which is capital W, small b. This is what we talked about last time. So how many do we have in that area, not per unit area, in the natural area? Well, as you can probably guess, we've got some area A here, and we've got a flux density, which remember is the amount of field lines we have per unit area. That's kind of a way of thinking about it. To find the magnetic flux, we have to times the density, magnetic flux density, by the area. This can be written like that, remembering that is the symbol for flux, and B was a symbol for magnetic flux density. Tricky here. Maybe some flashcards will be useful because two very similar things, they are very different. Or you can think of it as that looks like a TIE fighter from Star Wars, and BA, British Airways. God, I don't know if that might help. So there's your equation. And there's the units. Remember that a Weber is a unit for flux, magnetic flux, and that's equal to a Tesla meter squared, because they're times together there. Now, sometimes these field lines will not be perfectly right angles to the area. And that came up in that definition there. If it's not, again, we're going to have to take the component of that magnetic density, that is right angles to that. And we'll see how that comes in here. Also, there's a concept called magnetic flux linkage. And this is quite an easy one, and it's involved with a coil of wire. Often there's going to be a coil of wire in physics, and N there just refers to how many times we've wrapped that coil around. Now, let's take this coil of wire here, which has a kind of area here, and the field lines are coming in at a small angle theta. This here is kind of normal to the area of the coil. So imagine an area of the coil, this line here is drawn normal. Now, given that, as we mentioned earlier, magnetic flux is equal to magnetic flux density times area. Well, if we're talking about the magnetic flux linkage, which is just when you times the magnetic flux by the number of turns, then we're just going to get the equation BAN. We times both sides by n, basically. This here is a useful thing that we'll use in future topics. So magnetic flux linkage. Normally you write N followed by the symbol for magnetic flux linkage. However, if it's not at right angles, we need to take into account that we want the component of this. Think about this. If this is coming down like this, of a certain size, we want this component here, the component that's perpendicular to that face of that coil. If you draw up a triangle, you can quickly work out that if you do cosine theta times by the magnitude of this, you're going to get the size that is perpendicular to that area. So that's where this comes in here. So this equation can be written out as that. And there it is at the bottom. Nice and obvious. Remember, you can just copy out the ends, and then you've got magnetic flux is equal to BA cosine theta, which is useful.